We're going to go over ionization energies and electron affinities again. Remember, ionization energy, you're going to make a cation. So Na is going to go to Na plus and 1 electron. That you need to know is an ionization energy, making a cation. All right, and so if you have sodium, which is a neon, and a 3s1 for the electron configuration of sodium, when you take an electron away and become Na plus, now you are the noble gas core. And so if you try to take sodium plus, which has the neon electron configuration, and you try to make Na plus 2, this is a very large jump in ionization energy. Anytime you're taking the electron out of the noble gas core, you're going to have a huge jump in energy. All right, and ionization energies, remember, they increase as you go to the right, and they decrease as you go down. So if you're doing ionization energy, it's going to increase as you go to the right, and it's going to decrease as you go down. So that's the periodic trend. There's a couple of blurps in there, but that's the general trend that you would follow. All right, and so here again, the dramatic increase or the large increase, that's when you take an electron from the noble gas core. And so the next one shows when you take that from the noble gas core. All right, so lithium, which is in column 1, so this is in the first column, you can take the 1 out, but the second one has a large jump. Beryllium, which is in column 2, you can take the first one out, you can take the second one out. The second one usually takes about twice the energy as the first one. Then when you try to get the third one out, because it's the noble gas core, you have a large jump in energy, a huge increase in energy. And so that's what this is showing. All right, and so you have boron, you take out the first 3, and then when you take out the fourth one, that's when you have the noble gas core, that's when you have your large, dramatic increase in energy. So you have that when you're taking the electron out of the noble gas core. All right, so again, when we're doing electron affinities, remember here we're making an anion. All right, so now we're looking at, let's say, fluorine, and we want to add an electron to become F minus. So you have to know that ionization energy is making cations and electron affinities are making anions. And here's where you have the noble gas core after you add the electrons. So you have a 1s2, 2s2, 2p5. When you add an electron, now you have 1s2, 2s2, and 2p6, which is the electron configuration of a noble gas, and that is very stable for all of the halogens, everything in column 7. That's the -1 column. It's the -1 column because when they get 1 electron, now they all have the electron configuration of a noble gas. All right, and so a positive energy change, so the energy of that reaction, endothermic indicates the anion is unstable. All right, and so with the metals, they don't want to be anions. And so when you have a metal like sodium, to make a sodium minus, that does not want to happen, and that is endothermic. For your halogen, that is very stable, and you're going to have a large negative number. You're going to have an exothermic reaction. All right, because it's going to be a stable anion. All right. All right, so your metals and your nonmetals, remember you have your metalloids. If you look at your periodic table, all right, so you got your metalloids that go like this. All right, so your nonmetals are up here, and all these down here are metals. All right, hydrogen is over here pretending to be a metal, but it's really a non-metal, but that's the only one that doesn't fit in that. All right, so the metalloids, they cut down like a ladder down your periodic table. To the right, you have your nonmetals. To the left, you have your metals. All right, so now we're going to burn our different metals like magnesium. All right, and so when we burn magnesium, just like we did in lab, we get magnesium oxide. And we knew that because magnesium, this is the +1 column, this is the +2 column, +3 column, this is the organic column. Then you got your -3, your -2, and your -1. All right, so oxygen is in the -2 column, magnesium's in the +2 column. And so that's why we get MgO. So we can predict all of the oxides that we would get for a metal if we took sodium, Na, and we burned it in oxygen. We would get Na2O because Na is +1, oxygen's -2. To balance that, we need 2 there and 4 there. All right, so back to test 1, we can make our different compounds because we have the charge of the columns when we burn our metals. All right, if we're burning tin, remember when we had tin, we remember that tin came in 2 oxidations. So when you burn tin, since we memorized that tin is +2, you would get SNO, and tin is +4, you would get SNO2. All right, so back on that test 2, I think, test 1 maybe, I'm not sure. Tin is +2 and tin is +4. And so when you burn it, you're going to get 2 oxides for tin. All right, so to balance this one, we have a 2 in front here and a 2 in front there. All right, and so the other ones, we know iron is +2 and iron is +3. And we know that copper is +1 and copper is +2. All right, so those 3, we would get 2 different oxides. All right, so all of them in column 1, you would get 1 oxide, column 2, 1 oxide. And when you get to column 3, well, it may be more than 1 oxide depending on the different oxidations. All right, but we can get the oxidation numbers from the elements that are metals, and we make that with a -2 oxygen. The problem is when we burn nonmetals. So if you burn carbon in oxygen, well, carbon's in the +4/-4 column. All right, so when carbon is going to be burned, we all know that that gives us carbon dioxide. But we also have another oxide of carbon, and that's carbon monoxide. So carbon will also give carbon monoxide. All right, so you can get 2 different oxides for your nonmetals. And that is going to be pretty consistent for all of your nonmetals. All right, so when we take our CO2 and we add water to that, so you burned a bunch of stuff and now it rains. What happens? Well, you get acid rain. All right, you get carbonic acid, H2CO3. All right, if you had a bunch of carbon monoxide and you had a rain with water, you still have acid rain, but it is carbonous acid, H2CO2. All right, so you're going to predict your oxides of your nonmetals by knowing the ic acid and the us acid. So back to test 1, where you had to memorize the ic and the us acids. All right, so ic acids and the us acid. So you need to know those again. Memorize your ic and your us acids. Know them again. All right, because otherwise you're going to look at phosphorus here, and you're going to say, all right, I'm going to burn phosphorus. What am I going to get? Well, phosphorus is in the -2 column, and oxygen's in, or the -3 column, oxygen's in the -2 column. You cannot predict it. Metals you can predict. The columns are positive and oxygen's -2. Non-metals, what you have to know is what I have circled here. You've got to know the ic acid and the us acid. And we have to go back to oxidation numbers. All right, so let's look at burning phosphorus. So P4 is phosphorus plus O2. All right, so again, this is in the -3 column, that's in the -2 column. That is not how we can predict an oxide. What else do we know about phosphorus? Well, it comes as phosphate. All right, and so phosphate is your PO4 -3. You need to remember that again. That's your phosphate. All right, and then the phosphite is PO3 -3. That is the 8, and this is the ite. So bring out those flashcards again. Make sure you know your your 8s for your different polyatomic ions, and then of course take off an oxygen. Do not change the charge, and you have an ite. All right, because 8 goes to ic acid, H3PO4, that's phosphoric acid. And your H3PO3, that is your phosphorus acid. All right, so you need to know the, well, it doesn't matter, the 8 and the ite, or the ic acid and the us acid. I usually do those so that they're the same. It doesn't matter. But that's what you're going to get when you have your nonmetal oxide reacting with water. All right, so what we need to know is H3PO4. Oxygen is -2 oxidation, so that's -8. Hydrogen is +1, so that's +3. All right, and so we have a +5. So now we can make an oxide. When you do the oxidation numbers for your nonmetals, they are going to be positive. Now you can react that with a -2 oxygen and predict the oxides. All right, and so we know that the P is going to be +5 and the O is going to be -2. Again, to make a neutral compound, you can put that as a subscript, that as a subscript. We have P2O5. That gives us a -10 and a +10, a neutral oxides. All of your burning of your different elements are going to give neutral oxides. And to balance it, we put 2 here, we put 5 here. All right, the us acid is H3PO3. We're going to do the exact same thing. -6 for the 3 oxygens, +3 for the 3 hydrogens. All right, so here we have a +3 phosphorus. So phosphorus is +3. We can predict the oxide with an oxide that is -2. The common multiple, least common multiple is 6. And so we're also going to burn phosphorus in oxygen, and we're going to get a P2O3. P2O3, that is a -6, that is a +6, because each of these P's are a +3 oxidation. All right, to balance that, 2 here, 3 there. So those are our 2 oxides. When you take your oxide, P2O5, and you add H2O, this is where it's important to know the phosphoric acid. All right, this is where you're going to get H3PO4. To balance that, we need 2 here, and we need 3 here. When we take our P2O3 and add water, we get H3PO3. All right, and so we need a 2 there, and we need a 3 there. All right, so non-metal oxides. To predict the oxide of a non-metal oxide, you have to know the ic acid and the us acid. Those are the 2 oxides you're going to get. You also know when you take a non-metal oxide and you add water, you're going to get an acid. So non-metal oxides are acidic. All right, you blow into water, you're going to make that water more acidic. You're expelling your CO2. All right, and so you have a non-metal oxide, you add water, you're going to get an acid. All right, now when we take our magnesium oxide and we add water, we are not going to get an acid because magnesium is a metal, and metal oxides are going to give, plus water, are going to give a base. And that's going to be MgOH sub 2. All right, so you have to know a non-metal oxide and you add water, it's going to be acidic. A metal oxide and you add water, you're going to get a base. All right, so non-metal oxides, all right, in order to get the oxide, you have to know the ic acid and the us acid, be able to get the oxidation number to get your oxide. Your metals, they're right on the periodic table. What the oxidation number, the charge of that, is in the +2 column, it's in the +1 column. All right, so they are positives, and you can get that by your ionic compounds. All right. So we're going to go through all of the different groups on the periodic table. Again, a base oxide, that means you're going to have a metal. Anytime there's a metal connected to oxygen and oxides are neutral, you're going to get a base when you add water. Acidic oxides, that's when you have a non-metal oxide. All right, so your metal oxides are going to add, when you add water, be basic. You're going to get the hydroxide. Your non-metal oxides, you add water, you're going to get an acid. Starts with H. All right. Now, there's a bunch of exceptions to this, but we're going to stick with all metal oxides are basic on the test. All metal oxides are basic. All non-metal oxides are acidic. And to get an amphoteric oxide, you have to have a metalloid. So when you use a metalloid, then you're going to get both an acid when it reacts with the water, and you're going to get a base when it reacts with the water. You're going to get both of those. All right, so metal oxides are going to be basic. Non-metal oxides are going to be acidic. Metalloid oxides are going to be both. They're going to have characters of both the metal and the non-metal, and so they're going to have both acidic and basic reactions with water. All right, so we did group 1A. That's your sodium-potassium group. So we did sodium. All right, so we added oxygen, so that's in the +1 column. And so you had an Na in the +1 column, and you have oxygen in the -2 column. Again, the 2 goes there, the 1 goes here, and just like before, Na2O is our neutral compound. And so any metal coming off of group 1A is going to have 2 of the metals to 1 of the oxygens because they're all +1. So 2 there, 4 there to balance that. All right, so again, hydrogen is a special case. Hydrogen is a non-metal that likes to react like a metal. All right, group 2A, we already did this one too. So now you're talking about your beryllium, your calcium, your magnesium. We did magnesium and we burned it. And we did this in lab as well. You get magnesium oxide. All right, a 2 there and a 2 there. So magnesium is in the +2 column. Magnesium's in the +2 column. Oxygen's in the -2 column. This doesn't work very well because if you put the formula is Mg2O2, that is not correct. The correct one is the least common multiple, and that is going to be a 1-to-1 ratio, and so it is MgO for the formula. So right here, every metal in group 2A is +2, and oxygen's -2, and so they're all going to be in a 1-to-1 ratio in their neutral oxide. All right, so group 3A. All right, so boron is a metalloid. All right, and so the rest of them are metals. All right, so we're going to go with what I said before. Metalloids, we're going to say that they are amphoteric. All right, so on the test, if you have a metalloid, it's going to be amphoteric. I told you there's going to be a lot of exceptions to this, and since these are metals, I'm going to call them basic. All right, so I'm going to not do what they are in practice. I'm going to do what they are in theory. In theory, when you are a metalloid, you act as a metal and a non-metal, and so you're going to be amphoteric. When you are a basic oxide, when you're a metal oxide, you're going to be basic, and I'm going to stick with that on the test. All right, and so group 3A oxides are basic. The only one that has some acidic character is the metalloid boron. All right, so they're in the +3 column. So you have your B2O3, and when you add water, you're going to get the BOH sub 3. It's in the +3 column. All right, and so to balance that, you're going to need 2 here, and you're going to need 3 here. All right, so there is your boron giving the base. Now boron giving the acid, B2O3 plus H2O. What you see here is you got -6, you got +6. So the boron is a +3. All right, and so you're going to have an H, a B, and an O in order to give a B a +3. you need one H and you need two O's. All right, and so you would have your acid, because it has to start with an H, as HbO2. Any acid that gives boron a +3 oxidation is acceptable. Acid means it has to start with H. Okay, yes. All right, and so your basic oxides, your Al2O3, it's just going to give your aluminum hydroxide, AlOH sub 3. All right, and so to balance that, we just need a 2 here and a 3 here. And same with the gallium oxide as well. Those are metals. Metals are going to be basic on the test. If it's a metal, it's basic. If it is a metalloid, it will have both acidic and basic properties. All right. All right, so carbon is a nonmetal, so silicon and germanium are metalloids. All right, so here we have two that would react both as an acid and a base. All right, and so when you get below that, you're going to have your bases. Again, the bases, the metals are going to be basic. All right, so carbon, again, here we already did carbon. We know we're going to get CO2 when we burn it, and we're going to get CO when we burn it. And you're going to get the same thing for all of your various group 4A non-metals. All right, now your metals, we already did tin, and we also could do lead. It's the same, but we have SNO because we know that tin comes +2, and we also have SNO2 because tin also is a +4 oxidation. All right, so now we're with nitrogen and we are with phosphorus. All right, nitrogen and phosphorus. So you might think that they're different, but they're not. If you remember, nitric acid is HNO3, but phosphoric acid is not HPO3. It is H3PO4, but I said they are the same. Well, they are the same. When we do the oxidation numbers, we have 3 oxygens here, that's -6. 1 hydrogen +1. So N here is +5. We already did the phosphorus, we'll do it again. This is 4 oxygens, that's -8. Hydrogens +1, so that's +3. Phosphorus also +5. They are the same. They will give the same oxide. And so the ic acid is going to give the R2O5, just like we did with phosphorus. Nitrogen would work the same because we have nitrogen plus oxygen. And so again, we just showed up there that nitric acid, N is +5, O is -2. And so you're going to get an N2O5, just like we got a P2O5. When you take your N2O5 and you add water, this is a non-metal oxide, it's going to give an acid, you're going to get HNO3. To balance that, we need A2 in front of the HNO3. All right, and so we already did this one for your phosphorus, and that works exactly the same. But you have to know that nitric acid is HNO3. You have to know that phosphoric acid is H3PO4. All right, now sulfur is not going to burn, or sulfur is going to burn. Oxygen is not going to burn in oxygen. Sulfur is going to burn in oxygen. All right, so when we take sulfur and we don't know what we're going to get with sulfur, we have to know sulfuric acid, H2SO4. So that's what you have to know. You have to know H2SO3. You need to know sulfuric acid, and you need to know sulfurous acid. Then you have to know how to get the oxidations. Oxygen is -2, so that's -8. Hydrogen is +1, so that's +2. So sulfur here is a +6. Same thing down here. You got 3 oxygens, -6. 2 hydrogens, +2. This sulfur is a +4. So those are the 2 oxidations that you're going to have for sulfur. So when you take sulfur and you add oxygen, and sulfur is an octamer, you're going to get SO3. How do you know you get SO3? Well, because oxygen is -2, so that's -6, and sulfur is +6. And so you have a +6 sulfur. And the other one, you take S8 and you burn it, you're going to get both of these. You're going to get an SO2. How do we know it's SO2? Well, because oxygen is -2, so that's -4. Sulfur is a +4. So once you have this, you make a neutral oxide with that oxidation. And when you take your SO3 and you add water, you get H2SO4. And that is already balanced. When you take your SO2 and add water, you get your H2SO3. And that is already balanced. All right, and so everything in that column is going to work the same. All right, finally, the halogens. Again, halogens in the -1 column, that's not going to work. You have to know the ic and the us acid, HClO3. All right, so that is your chloric acid, HClO2. That is your chlorous acid, and that would be the same as you put your iodine in there, bromine in there. That's your halogens. All right, we need to know this so that we have an oxidation number. And so, again, we have a -6 here. We got a +1. Chlorine here is a +5. You got a -4. You got a +1. Chlorine here is a +3. So this is going to work exactly the same as our nitrogen and phosphorus. So when you take your chlorine and you burn it, you're going to get two products. One where it's a +5, one where it's a +3. So you're going to have the Cl2O5, just like you had the N2O5. And you're also going to get the Cl2O3 in order to get the +3 oxidation. So 2 there, 2 there, 5 there, 2 there, 2 there, 3 there. All right, then you take your Cl2O5, which is a non-metal oxide. All the halogens are non-metals. And you add water, and that's when you get your chloric acid, HClO3. And to balance that, we need 2 here, and then that's balanced. If you take your Cl2O3 plus water, you get your chlorous acid, HClO2. And again, to balance that, we just need a 2 in front of that. All right, so in order to predict your oxides, you have to know the ic acid, and you have to know the us acid. And you will get from that the oxidation numbers of the nonmetal. From that, you get a neutral oxide. And then when you add water, all right, then that neutral oxide is then going to react with that water to give you the ic acid for the first one and the us acid for the second one. And then finally, your noble gases, they are unreactive. So if you try to burn your noble gases, you're not going to get anything from that reaction. They will react in later chapters when they form complex ions, and we will do that chapter 17, I think it is. All right, I think that, okay. That is the end of the material for the test on Thursday. Let's see here. All right, so for exam 4, you're going to be given this equation. This is the only equation given. It's not really right on that, is it? Okay. All right, so you also have to know E is equal to H nu and C is equal to lambda nu. Again, all of your constants are given, so speed of light is given. It's given to a ridiculous number of sig figs. I would round that to 4 sig figs, or you can use the whole thing if you want to. But that is going to be given on the test. You don't need to know any of the constants. All the constants will be given. Right now, the only equation that's going to be listed is this one, and that's the equation where your electron is going from say n energy level of 4 down to n energy level of 1, and then you just plug in your constants. All right, H is given right there, Planck's constant, Rydberg constant also given, it's right there. And then I just said 4 squared, I said 1 squared. You simply push the buttons and you get your frequency. All right, so that is going to be given. There's some problems to do. Okay. All right. So if we go to our practice exam 4 test, and we have copper. And so the question is, give the electron configuration of copper and the 4 quantum numbers. All right, so copper. So you go to the periodic table, you find copper. All right, so copper is right here, number 29. All right, so we find copper. All right, and so you need to know that you start, the 1s is right here. All right, so there's the 1s, 2s, 3s, 4s, 5s, 6s, 7s. All right, come over here, the first p, these are the p's. So boron is the first p, so that's a 2p, 3p, 4p, 5p, 6p, 7p. All right, and so the s and the p's are in the same energy level as your period number. So the first period is 1s, second period is a 2s and a 2p. Note the third period is a 2s and a 2p. The d is not here in this third period. The d is in the fourth period, but the d starts with 3, s starts at 1, p starts at 2, d starts at 3. This is the 3d. This is the fourth period. This is the 3d. This is the fourth period. This is the 3d. That's how it works. The d is always 1 less than the period number. If your period number is 4, the d is 3. If your period number is 5, the d is 4. It's always 1 less. So you have to know that this is the 3d, then this is the 4d, and this is the 5d, and this is the 6d. For the f's, you have to subtract 2 because s starts at 1, p starts at 2, d starts at 3, f starts at 4. But it doesn't come in until the 1, 2, 3, 4, 5, 6 period. So in the 6th period, you have the 4f. And so the f is always 2 less than your period number. So that's the 4f, and the one below it is then the 5f. And so s starts at 1, p starts at 2, d starts at 3, f starts at 4. All right, so when we are at copper right here, number 29, I know that I'm in the 3D because I know D starts at 3. And then I just count it over. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is a 3D9. All right, but there are the exceptions, and that is one of them. So remember your exceptions. So your copper is going to be argon, which is 18, and then a 4s2, and then a 3d9, except this is copper. So you have 5 exceptions that you have to know. This is one of the 5 exceptions. To your buildup rule. So we go back to our periodic table. All right, your exceptions are your CR, number 24 here, and MO, number 42. Those are 2 are exceptions. And then this whole column of copper is an exception. All right, copper, silver, and gold. This one I'm not going to give, but that, well, I didn't give it as an exception, so leave it the way it is. All right, so copper, silver, and gold. All right, so those are exceptions. So you have to remember those 5 are exceptions to the buildup rule. All right, and so what happens is your 4s is full, and then your 3d has 9. Remember how you put in 9 electrons. 1 goes in each one, Hund's rule, the bus seat rule. And then you pair them up until you hit 9. And so that's a 3d9. So this is not the actual ground state for copper. The ground state is that it is more stable if you have a full d subshell. And so this electron isn't there, that is here. And so the actual electron configuration for copper is an argon, which has 18 electrons, and then a 4s1, and then a 3d10. All right, and so that, again, is one of your 5 exceptions. Everything else is just as the buildup rule would predict. Well, that's not true. These are the only 5 exceptions you need to know. The rest of them are graded on, is that the way that the buildup says it will be? Right? There's many other exceptions. We don't need to know any of those other exceptions. Everything else follows the buildup rule. We will go with that assumption that everything else follows the buildup rule. All right, and so then it says, and the 4 quantum numbers for the last electron that was put in. All right, so that's when I will accept more than one answer, because you could interpret that one of 2 ways. So you could say the last electron that went in was the 3d9. That was the last one that went in, and then the 4s2 then moved after that last electron went in. So let's do both of those. We'll do a 3d9 and 3d10, because I would accept either answer for the 4 quantum numbers. All right, and so the first quantum number is whatever number is listed, and that is a 3. Then the D, you have to know when you have the second quantum number, 0, 1, 2, 3, 4, to infinity, that is your S, P, D, F, G alphabetical order. All right, and so since we're in the 3D, D's number is 2. And so that is a 2. All right, and so we put in the 5 orbitals. We've already wrote it out. Here's the orbital diagram. All right, and so we number them. And remember that the orbital in the center is always orbital number 0. Then you go 1 and 2 to the right, and then you go -1 and -2 to the left. So when we're doing number 9 is this one. We're going to do number 9 first. First, we're going to do 3d9, then we will do 3d10. All right, and so it is in your orbital number 1, and it is going spin down. When we do the 3d10, now we're looking at this one. The only difference is it's in orbital 2. And so 3-2 is the 3D. Now it is in orbital 2 with a spin that is down. So on the test, I would accept this set of quantum numbers. If you say that the 3D10 was the last one that went in, I would accept this one if you said that the 3D9 was the last one that went in, and then the 4S1 was promoted up to the 3D10. Again, that's semantics. So either way would be fine. I don't care if you're given the last electron as a 3d9 or 3d10, but the only correct electron configuration is this one. And of course, if when you see this answer, it's always given in number order. I don't care what order you put it in. I would prefer it to be in this one, although I don't write it this way. But if you're asking me which way should I write it, I will say this way every time. So then when I say give the electron configuration of copper +1, that means you have to remove an electron. And again, you don't remove electrons the same way that you put them in. You remove them out of the highest N energy level. And so if you write it in number order, then you know to take them out from the right to the left. And so you have copper. All right, so you have your copper +1, and so that is an argon. That is a 3d10, and then there's no 4s. You don't write 4s0. You'd have to write zeros for every other one that's there. All right, so if it's 0, you do not write it. There's no electron in it. You don't put that subshell with a 0 in it. That is where it is taken out. If you do a copper +2, that's the 2 oxidations of copper that are stable. And now you have no choice. You have to take it out of the 3D. And so now you have 3D9. And so those would be your copper and your copper +2. All right. Bromine. All right, when you want to find the oxidation or your electron configuration of bromine, again, you got to find it on the periodic table. All right, and so when you find bromine, it is right here. It is number 35. First prior noble gas is argon. All right, after argon comes 19, which is the 1s, 2s, 3s, 4s. So we have 4s2, then we have 3d10, and then we have the 4p5. All right, and so it is number 35. Bromine, so that's argon, 4s1, 4s2, 3d10, and then the 4p5. When you add them up, you have your 18 here plus your 17 here, and that gives you the 35 neutral. You have a neutral, that means your protons and your electrons have to be the same. Again, I will accept this as the correct answer. Better way to write it is argon, and then the 3d10 should be written first, then the 4s2, then the 4p5, because when you remove electrons, they would be removed out of the 4p5, and then if you took all of those electrons out, then you would remove them from the 4s2. Then if you removed all of those electrons, then you would remove it from the 3d10. All right, now we need our 4 quantum numbers for the 4p5. All right, so you should, a lot of times it's going to ask for the orbital diagram. And so for the 3D to fit in 10 electrons, of course, that has to have 5 orbitals. All right, so this is your 3D, and there's 10 electrons. And so remember, an orbital can only hold 2 electrons. And it can only hold 2 electrons if you have one that has a spin up, and then the next one that comes in is a spin down. The S only has 1 orbital, and it holds 2 electrons. First one spin up, second one spin down. The P's hold 6 electrons, which means they have 3 orbitals. Again, the first one has to go in, spin up, Bus-Seat rule, Hund's rule, 1 in each, and then the next one has to go in, spin down until you hit 5 electrons for your 4p. All right, and then to get the 4 quantum numbers, again, when you're numbering your orbitals, the orbital in the middle is always 0, and negatives to the left, positive to the right. All right, if it's just 1 orbital, it's a 0. The one in the middle, 0, and then a 1, and then a negative 1. All right, and so when you do that, of course, your first number is whatever number is given, and this time it's a 4. P. Now, P, again, your L can be 0, 1, 2, 3, 4, out to n minus 1. All right, so that's S, P, D, F, G, alphabetical order. So when it says P, you know that your second number is a 1. So 4, 1 is a 4p. All right, now you need the orbital number. In this case, this is the electron, the 5th electron. And so it's in orbital number 0, and it is spin down. So those are the 4 quantum numbers for the 4p5. The next one is SR. So we have to find SR on the periodic table. All right, SR right here, number 38. All right, so once you find 38, we know that that is in an S, not the 1S, not the 2S, not the 3S, not the 4S, but the 5S2. So we can look at the periodic table and know that that is a 5S2. First prior noble gas is Kr. So it's simply Kr 5s2. All right, and to get the 4 quantum numbers for the 5s2, again, you draw the orbital diagram. S only has 1 orbital, and if you only have 1 orbital, it's a 0. If you have more than 1 orbital, the one in the middle is 0. All right, and so the first number is a 5. So first quantum number is simply the energy quantum number. That is the number listed first. That is a 5. Now the S. Now you got to go to the L quantum numbers. Remember, 0, 1, 2, 3, 4, and that goes to infinity or to n minus 1. So if you go up here, you see that the first one is S. You can write it every time or go back up and see where you wrote it down. So this is your S, P, D, F. All right, so that is then a 5 and a 0. All right, there's only one orbital, and so that orbital number has to be a 0. So 5, 0, and then 0. That's the only number you have for an s orbital. And then the second electron has a spin down, so it is a minus 1/2. So a 5, 0, 0, negative 1/2. That is the 4 quantum numbers for your 5s2, the last electron put in for SR. All right, you go to the next one. ER. So now we got to go find ER on the periodic table. And ER is right here, number 68. All right, bottom left here, ER is number 68. So the first prior noble gas is Xe54. All right, so 68 is what we have to go to, 54. So then we go to 55. 55 starts 1, 2, 3, 4, 5, 6s. All right, so we have Xe, then we have the 6s, 6s2, and then we go down to 57. 57, that is the first F subshell. Remember, F starts at 4. It is 2 less than your period number. Period number 6, this is the 4F. And then we got to count across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that is a 4F12. So we have a 6s2, 4f12, and that is for ER, and that was an XE. All right, so again, if I wanted ER plus, and you wrote it this way, if you take it out of the 4f, you have the wrong answer. And so it is an XE, and then it is a 6s1, 4f12. That's why it is preferred to write it as an XE and then a 4f12 and then a 6s2, so that when you take one out, you don't forget to take it out of the one on the right there. And so that would be a 4f12 and a 6s1. These answers are exactly the same to me. I don't care which way you write them. The key is make sure you're taking the electron out of the highest N energy level. You do not take electrons out to make cations the same way that you put them in. You take them out of the highest N energy level. The reason why you would write it this way is you remove them when you go that way. You would take the first 2 electrons out of the 6s, then you would take the electrons out of the 4f. All right, but we still need our 4 quantum numbers for the 4f12. All right, so when you have your S, that is 1 orbital. Here's your 6s2. And now you have to have your 4f12. You have to know that F has 7 orbitals. It holds a maximum of 14. And you have to know that the one in the middle is number 0. And then you go 1, 2, 3 to the right. You go -1, -2, -3 to the left. And now you have to put in 12 electrons. You have to follow the bus heat rule, Hund's rule. You put 1 electron in each orbital before you would come back and pair them up. So that's 7, and then 8, 9, 10, 11, and 12. So this is the 12th electron. All right, so the first number is the 4. That is your energy level. F, we go back up. 0, 1, 2, 3, S, P, D, F. And so F is a 3. All right, and then now we stopped in orbital number 1. Orbital number 1, and the spin was down, -1/2. And so your 4f12 has the 4 quantum numbers 4, 3, 1, -1/2. Right. unknown element number 130. All right, so we need the electron configuration of element 130. All right, so 118 is as high as we have here. All right, so after 118, you're going to then go to 120, or 119, which is going to be right here. And so that is the 1s, 2s, 3s, 4s, 5s, 6s, 7s, 8s. So UUO. So we need unknown element number 130. UUN is 118. All right, and so here's where you have to draw your buildup rule. Although we know that that is going to be next is an 8s2. The problem is, what is after the 8s2? All right, and so to do this one, you need to do the buildup principle. And so you can do this any way you like. I prefer to do it this way, 1s2, and then I do 2s2, 2p6, and then I do 3s2, 3p6, 3d10, and then I do a 4s2, 4p6, 4d10, 4f14, and then I do the 5s2, 5p6, 5d10, 5f14, 5g18, and then I do the 6s2, and the 6p6, and the 6d10, and the 6f14, and the 6g18, 6h22, all right, 7s2, 7p6, 7d10, 7f14, 7g18, 7h22, 7i26, all right, and it's going to keep going to infinity. All right, and so, and then 8s2. All right, so when you fill it, first you fill the 1s2. That's the one you fill first. Then you fill the 2s2. Then the 2p6, then the 3s2. Then the 3p6, then the 4s2. Then the 3d10, then the 4p6, then the 5s2. Then the 3d10, then the 5p6, then the 6s2. Then the 4f14, 5d10, 6p6, 7s2. Then the 5f14, 6d10, 7p6, 8s2. This is where we're at. We are at the 8s2. So when you add all these up, we're at 120. After that comes the 5g18, then the 6f14, then the 7d10, then the 8p6, and then the 9s2 if you want to keep going. And then after that, you would do this one, fill that line, and then finally the H would come in. All right, so the key is after your 8s2 comes the 5g18. All right, but we only need 10 of them, so that would be a 5g10. So you have to add up to 130. You got 118 for your last noble gas here, which is UUN. All right, then comes the 8s2. Now you're at 120, and then the 5g10. Now you're at 130. All right, and so again, with your S, you have one orbital because it holds 2 electrons. For your P, you have 3 orbitals. It holds 6 electrons. D has 5. It holds 10 electrons. F has 7 orbitals. It holds 14. The G is going to have 9 orbitals because it holds 18 electrons. All right, and so here is your 5G10. The one in the middle is 0. Then you have your 1, 2, 3, and 4, and your -1, your -2, your -3, and your -4. All right, and so again, your first number is a 5. Then G, okay, so L, 0, 1, 2, 3, 4, 5, 6, and that is S, P, D, F, G, H, I. All right, so G is 4. Now you got to put in the 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This is the 10th electron. So that is in orbital number -4, and the spin is down. And so the 4 quantum numbers for your 5G10 are 5, 4, -4, -1/2. The only time you have to use this buildup chart is when your element is past the known elements on the periodic table. Otherwise, you can follow this right on your periodic table. But this can be used for all of them. You can use this buildup to give you every answer except for 5, the 5 exceptions. All right, so this one gives you the correct configuration of every element on the periodic table for the test except for the 5 exceptions. It also gives you the correct electron configuration for every unknown element that will be made eventually and be on the periodic table. All right. Next question. All right. All right, so we already did copper +1, bromine minus, and SR +2. So bromine minus. So we go back up to our bromine. The minuses are simple. You simply just add an electron, just like you would add the next electron. All right, so the only hard one here was the copper. For 1, it's one of the exceptions. You had to know that that is the exception and to pull the electron out of the highest N energy level. All right, so your bromine, you simply add an electron to it. And so Br minus is your argon. And then you have your, in the correct order, 3D10, 4S2, and then a 4P6. So we just had to add an electron. When you're negative, you add, just like you would do the buildup rule, just add another electron. And for your SR, that one is easy as well because you're only looking at these 2 electrons and you remove them both. So SR +2 has the electron configuration of Kr. We took out the 2 5s electrons. So those are relatively easy. The copper one is the one that everybody misses because most people will pull it out of the 3D. That is the wrong orbital to pull the electron out of. The highest number orbital, the highest energy orbital is where you take the electron out of. And that's why they write them in number order, so that you remember to take it out of the highest orbital number. All right, so this one is interesting. Number 2, you have to label it as an anion, a cation, or neutral. Every cation, every anion, and every neutral have one ground state. There's one ground state for a neutral. There's one ground state for an anion. There's one ground state for a cation. So you need to know what the charge is and say, is that what I would write for the electron configuration? If it is, it's the ground state. If it is not, then it's going to either be an excited state or a forbidden state. An excited state is an orbital that exists. You put it into some higher orbital, but that orbital does exist, and that would be an excited state. A forbidden state is you put it into something that does not exist, or you put more than 2 electrons in an orbital. If you try to put more than 2 electrons in an orbital, then it is forbidden. So when you have hydrogen and that's 1s1, and you look at your periodic table and you say hydrogen 1s1, you're like, yes, hydrogen should be 1s1, 1 electron, 1 proton, neutral. All right, so it starts off nice and simple. All right, so you've got your 1s1, neutral, ground state. So that is how you would write hydrogen, neutral and ground state. Now in part B, we have hydrogen still, but now it's 1s2. All right, hydrogen always has 1 proton. It is atomic number 1. That never changes, 1 proton. Now it has 2 electrons. That means it is an anion. All right, and so for part B, it is an anion. And if I said, write the electron configuration of H minus, you should write 1s2. And so this is the ground state for the anion. All right, so this is the ground state hydrogen neutral. This is the ground state hydrogen anion. All right, so Ti, you look at this and it says argon 2d4. All right, as soon as I see 2d4, I say forbidden, because D starts at 3. There's no such thing as a 2D. All right, so S starts at 1, P starts at 2, D starts at 3. This does not exist. And so that one is forbidden. All right, so we find Ti on the periodic table. All right, so Ti is right here. It should be argon, and then it should be 1, 2, 3, 4s2, 3d2. So it should be 4s2, 3d2. All right, so it should be 4s2, 3d2. So it should be argon and should be 4s2, 3d2. All right, so it has 22 electrons. So this is 22 electrons, 18 and 4, 22. If you're doing that over here, 18 and 4, that's 22. This is forbidden because there's no such thing as a 2D. All right, so it's neutral because it has the correct number of electrons. It has the same number of electrons as protons, so that makes it neutral. All right, but it's supposed to be 4s2, 3d2. This says 3d4. The 3d does exist. The 3d does hold more than 4 electrons. It holds up to 10 electrons. So you didn't put more electrons in that would fit. And so this is simply an excited state. All right, so we put the electrons in the D instead of the S. They fit there. That's not where they're supposed to go, but they fit there. That's an excited state. If you put them into an orbital that doesn't exist, a 2D, that is forbidden. All right, so here we have ZR, KR, 4D2. So when we look at our periodic table and find our ZR, all right, ZR is right here. So it should be KR and then a 5s2 and then a 4d2. So it should be a 5s2, 4d2. So it should be a 5s2, 4d2. The 5s2 is missing. That's because this has 2 less electrons than it's supposed to have. All right, that makes it a cation. Not only a cation, a +2 charge. So this one is missing 2 electrons. The 5s2 electrons are missing. So this is your ZR +2. Now, if I said to write the electron configuration of ZR +2, this is exactly what you should write. You should take the electrons out of the 5s2. That's the higher number. And so this is a ZR +2 in the ground state. That's exactly how you would write the +2 of ZR. All right, silver. Silver, again, that's one of our 5 exceptions. So we find silver right here, number 47. And so it is KR. And then we go down 1, 2, 3, 4, 5, S2. And then you have your 4D9, but we know that that is an exception. So it is a 5S1, 4D10, just like we did copper. It is the S1D10. All right, and so it is the S1D10. This is neutral, this is ground state. All right, so this is the exception, one of the 5. So that is the neutral ground state that if I ask for the electron configuration of silver, this is what you should write, neutral and ground state. All right, the last one here is iridium. All right, and that's 5, 4, and 5. Okay. So this is number 77 on the periodic table. So we go to our periodic table and we have iridium. All right, and so Xe is the first prior noble gas. After that, we have 55, which is the 1, 2, 3, 4, 5, 6s2. After the 6s2 comes the 4f14. After the 4f14 comes the 3, 4, 5d, and we count them over 1, 2, 3, 4, 5, 6, 7. 5d7. So we have a 6s2, 4f14, 5d7. So we have a 4, a 5, and a 6 if we write it in number order. All right, so this one is very tricky because it looks like it's the right answer. You got your S2, you got your 14, you got your 7. All right, 4F14 is right, 5D7 is right. Your S is supposed to be 6. This should not be a 5. This is a 6. When you do XE, you've already filled the 5S. Now you're putting 2 more electrons in it. So this is essentially a 5S4. This is forbidden. It is neutral, has the right same number of electrons as protons, but XE already has the 5S full, and that one is forbidden. And we will pick up there tomorrow.